Okay, so welcome to this first video in the playlist on vector spaces. Okay, right, so in this video what we're going to do is study the definition of a field. Okay, now just before we begin, what I want to do is firstly make an introductory remark about this playlist on vector spaces. Okay, so this playlist on vector spaces is designed to follow the playlist on group theory. Okay, so we are often going to rely on you having a working knowledge of group theory when we make definitions in this playlist on vector spaces. Okay, so if you do have a working knowledge of group theory, then you should be fine with this playlist on vector spaces. If you haven't studied group theory before, then you need to watch the playlist on group theory first before watching this playlist on vector spaces. Okay, so that's the first thing to say. The second thing to say is you might be wondering why in a playlist on vector spaces is the first video the definition of a field. Why is it not the definition of vector space? When in order to define a vector space we need to know what a field is. Okay, so that's why definition of a field is coming prior to the definition of a vector space. Okay, right. So let's now begin then with the definition of a field, but before we actually get into what a field actually is, let me firstly try and motivate what we're trying to do here. Okay, so once again, a field is a notion from abstract algebra, and in abstract algebra what we are trying to do is generalize notions that we had in classical algebra. So classical algebra is the sort of algebra you learnt in school. Okay, it focuses on certain number systems in particular. So in your school education you will have learnt the rational number system first. Okay, so all of the different fractions, and they have composition laws of addition and multiplication on them. Okay, so a great big set of symbols with these composition laws on. Then you might have progressed up to the real numbers. Okay, an incredibly complicated number system, but an incredibly powerful number system. And then if you went far enough, you will have learned about the complex numbers in school. Okay, and these are three incredibly important number systems, but they are just three number systems. Okay, the reason you learn them in school is because they're so important. The real numbers in particular, I mean physicists, engineers, chemists, they use the real numbers all the time to model real world structure. Okay, so they're very, very important number systems, but they are just three number systems. Okay, and in abstract algebra, what we're trying to do is generalize these concepts of building number systems, basically. Okay, we're acknowledging, okay, these are just symbols with these composition laws on. Surely we can create others apart from those ones. Okay, and that's what we're trying to do in abstract algebra. So in the video on definition of a group, we saw the concept of a group number system. Okay, and in a group number system what you did is you created a set of symbols that could be finite or infinite, and then what you did is you defined one composition law on that set of symbols. Okay, and that composition needed to obey a bunch of axioms that made it interesting, the four axioms of group theory. Okay, now in field theory, with the definition of a field, what we're going to do is create more complicated number systems. Specifically, what we're going to do is create number systems which have two composition laws on them. So they're going to be closer to the rational numbers and the real numbers and the complex numbers from classical algebra. In fact, we're going to see that all three of those number systems from classical algebra are indeed field algebras. Okay, right, so let's now begin then with the definition of a field. So we are defining a field, and a field is an abstract number system that needs to obey a bunch of properties that are going to end up making it very interesting. Okay, and a lot of these properties you will be very familiar with from classical algebra. You'll sort of recognize them. Okay, and really a big part of abstract algebra is just recognizing that these properties that you had in classical algebra aren't actually trivial, because you take them for granted in classical algebra, you just take them as obvious, but in abstract algebra we need to appreciate that they're not obvious at all. Okay, right, so then, the definition of a field. So a field is often denoted capital F. Okay, F obviously for field, just as a group was denoted capital G. Okay, and it fundamentally is going to start off as a set of symbols. Okay, so I'll denote this here. So we're going to have a set of symbols. So this set could be finite or it could be infinite. Okay, but it's just a set of symbols and you can make up the symbols. So that's the first fun bit, that you have to make up a bunch of symbols, and this is the set of symbols that you're going to use to build your number system on, basically. Okay, right. Now, to turn this into a field, at the moment it's just a set of symbols. To turn it into a field, you have to put on this set of symbols two composition laws that are going to obey incredible axioms. Okay, an incredible list of axioms. Okay, now, unlike in group theory where the composition laws could be called whatever you like, in fields the composition laws are always called the same thing. Okay, so the first composition law, which I'll draw here, okay, so here is its composition table, is going to be called addition. Okay, and it's going to be denoted in the normal way, plus here. Okay, so composition law number 1 is going to be called addition. Okay, so that's just the name for this first composition that you're going to create on this set of symbols. Okay, so quite simply what you're going to do then in this composition table is you're going to give absolutely all of the elements of the field a row in the composition table. So you'll put all of the elements of the field over here, and I'll get a new colour apart from red on here. Okay, so we'll have vivid purple here, so we'll put all of the elements of the field down here. We'll give every single one of them a row in this addition composition table. Okay, similarly what we'll do is we'll put all of the elements of the field up here as well. We'll give all of the elements of the field a column in this group composition, in this addition composition table. Okay, so we'll give all of the elements of the field a column up here. Okay, right, and then what we're going to go through and do is define what any element of the field added to any other element of the field actually is. So we'll have to go through and define all of the answers in this composition table. Okay, so what axioms then does this addition composition law need to actually obey? Well, basically, we can quite simply state this as the field, the set of symbols with just this addition composition law on it, is an abelian group. It needs to be an abelian group. Okay, so addition needs to obey the axioms of an abelian group. Okay, so this composition table that I've got here needs to obey the axioms of an abelian group. Now remember, the field is going to have another composition law defined over here, but if you ignore that one and just think about having this set of symbols with this addition composition law on it, then this needs to be an abelian group, and that's a nice easy way of stating all of the axioms that this composition law needs to obey. Okay, now just so that it's completely just so that the video is complete, I will actually now go through what this means. Okay, so I'll go through the axioms then that an abelian group composition law needs to obey, and which therefore this addition composition law is going to obey. Okay, so there are 5 axioms then that an abelian group needs to obey. 4 for a group, and then 1 extra one for being abelian or commutative. Okay, so we'll start off with axiom number 1. Okay, so axiom number 1, remember, says that all of the elements in the composition law here need to be from the field itself. Okay, so whatever little x and little y you pick from the field, so pick whatever little x and whatever little y you like from this set here, okay, it must be the case that if I add little x to little y, so if I compose these two together under addition composition, that answer must be another element of the field. Okay, so intuitively all that's saying is that all of the answers that I actually put in my addition composition table here, which I'll colour in yellow here, all of those must be back in the set basically. So you mustn't just put some new symbol that's outside of this set in as one of the answers in this composition table. Okay, so that's a very nice intuitive one. Okay, so that's axiom number 1 of an abelian group. Axiom number 2 is a complicated one, but we have got used to it because we have studied group theory for so long. Okay, and axiom number 2 is associativity. So axiom number 2, associativity, is about the composition of three things. So if you consider x plus y plus z, okay, now of course this composition table here for addition does not tell us actually how to compose three things together. It just tells us how to compose two things together. So if we want to compose three things together, the only way that we can actually give this meaning with our composition table here is to reduce it into the composition of two things at once, at a time basically. Okay, so the way that we can do that is by putting brackets here. So we can put x plus y, okay, and we can put brackets around the x plus y, and what this will mean is first we compose x and y together with the addition composition table, and then take the answer, whatever that is, which is an element of the field again, by axiom number 1 here, and then add that to z. Okay, so that reduces this composition of three things into composing just two things together at any one time. Okay, but of course there's another way of splitting the composition of these three elements down into the composition of just two things at once. Okay, and that's by putting the brackets around y plus z. So you could also put the brackets around y plus z here. And basically, axiom number 2 of this addition composition table for being an abelian group composition table says that these two things must be equal to one another for absolutely all little x, little y, and little z that you could take from the set capital F here. Okay, so that is the associative law, that when you want to add three things together, there is one and only one answer to that. It does not matter how you put the brackets in, basically, how you break the composition of three things down into the composition of just two things at any one time. Okay, so that's what we mean by the associative law, and we've spent a lot of time studying that in the form of group theory in the group theory playlist. Okay, right, so axiom number 3 then of an abelian group says that there must exist an identity element. Okay, now there is a symbol that we always use for the identity element of the addition composition law in a field, okay, and that is 0. Okay, so there must exist 0, which is an element of our set capital F, okay, such that if you add 0 to anything, it gives that other thing back again. So if you take 0 plus x, okay, that will equal x, and if you do it the other way around, if you do x plus 0, that will also equal x for all x is an element of the field F. Okay, so let's draw a picture for what this means. Indeed, let's add 0 into our addition composition table that we've got up there. Okay, right. So we'll have a row dedicated to the element 0. So here is the row dedicated to the element 0. I'm sorry, this is getting a bit squashed. And here is a column dedicated to 0. Okay, right, so this top one here, we're taking 0 and we're adding it to any other element of the field, and we're getting that other element back again. So this relates to this entire row here of the addition composition table. Okay, so this is saying take 0 here and then add it to any element of the field you like, and you must get that same element of the field back again. So what does that tell us about this row corresponding to the element 0? Well, it tells us that this must be an exact replica of what we've got up here. So you'll have all of the elements of the field appearing in this row, and they'll just appear in the same order that they do up here, basically. Okay, so any little x up here will appear down here in its column dedicated to it, basically. Okay, so that's what this top one means. Now the bottom one here, x plus 0 is equal to x for all x is an element of the set capital F. Okay, that is talking about the column corresponding to little 0. So you'll take any element of the field from here, you'll take the row dedicated to this element of the field, little x, and you'll add it to 0, and now you're looking at this column dedicated to 0. And again, what we know is that you must just get the same element of the field back again. So that tells us that this column must just be a replica of this portion here. So you'll have all of the elements of the field appearing in this column, and they'll all be in the same order as they appear on the side here, basically. Okay, so when you look at an element little x's row in this composition table, in the column corresponding to 0, its entry will just be itself, basically. Okay, right, so that's axiom number 3 of an abelian group then. Okay, now let's go on to axiom number 4 of an abelian group. So axiom number 4 of an abelian group says that for all elements of the group, so for all little x is an element of our set capital F, okay, it must be the case that there exists another element which is the additive inverse, the inverse of this element under addition. Now the additive inverse of an element is denoted negative x. Okay, so the negative number is going to be the additive inverse of an element, and this is why subtraction and indeed later on we'll see division are not separate composition laws. They are just part of addition and multiplication respectively. Okay, subtraction is not a separate composition law. It is just addition of the additive inverse, basically the negative of a number. Okay, so when you're subtracting, you're really adding a negative number, basically. You're adding on an additive inverse of something. Okay, right, so bear that in mind. So the rational numbers, the real numbers, and the complex numbers, they do not have 4 composition laws on them. They only have 2. Subtraction and division are part of addition and multiplication, respectively. Okay, so for any element of the set capital F, there must exist its additive inverse, which we'll call negative x, which is an element of the field capital F, such that if I compose these two together, okay, and I'll just highlight this in, okay, such that if I take x plus this other element negative x, I will get the additive identity back again, and if I do it the other way around, negative x plus x, okay, I will also get the additive identity back again. So there is some element of the field capital F which, if you compose it with little x either way around, will give the additive identity back again. Okay, and there'll only be one of these. Okay, for any element of the field little x, there will only be one additive inverse of little x. Okay, and the reason for that is that if there were more than one additive inverse of an element of the field, okay, it would break associativity. So let me show you this. Okay, so let's say, where can I put this? I'll put this over here. And I'm just wondering whether that is the best place. Actually, I'll just put it here. Okay, so I'll just move this up. So let's say that we have this element, little x, of our field, capital F. Okay, and let's say there were 2 elements which were the additive inverses of little x. Okay, so let's say x1 and x2 were both additive inverses of little x. Okay, so that means that you can compose little x with little x1 and little x2 either way round that you like, okay, and get the additive inverse. Okay, well what I could now consider is x1, x2. So the, whoops, and I'm thinking in group theory, I need to put addition signs in the middle there. I'm just thinking of putting them next to each other to denote composition, but in a field we need to actually put the addition composition symbol in there. Okay, so what I mean is x1 plus x2. Okay, right, so if I wanted to add all 3 of these together, well, what I'd have to do is split this down into composition of just 2 things at once. So I could put the brackets in the 2 places. So I could put the brackets around x1 plus x and then have plus x2 on the side, or I could do it the other way. So I could put the bracket around x plus x2, like so. Okay, and associativity tells me that these 2 things must equal the same thing, basically. But here's the problem, they're not going to equal the same thing, because if we look at this top one here, x1 plus x will equal the additive identity 0 by definition of x1 being the additive inverse of x. Okay, so that bit's gone to 0, and then 0 plus x2 will be x2, so the answer here will be x2. Whereas the answer down here, x plus x2, again that will equal the additive identity 0 just by definition of x2 being an additive inverse of x. Okay, and now have x1 plus 0, and of course that will just equal x1. And x1 and x2 were assumed to be distinct elements in the set capital F. Okay, so now I've got a contradiction of associativity not working. Okay, so if you had two additive inverses for an element of the field at capital F, then it will break additive associativity basically. So you can therefore only have a single additive inverse of any element of the field. Okay, right, and indeed that's true in a group. You can only have one inverse element, and it's going to be true for our multiplication composition law that we'll define in a moment, that again you can only have one multiplicative inverse when you do have an inverse. Okay, right, so only one additive inverse is what that is proving. You can't have more than one additive inverse, otherwise it would break associativity. Okay, so that's axiom number 4 then of an abelian group. Now let's go on to the fifth axiom. Of course, those 4 axioms are just the axioms of being a group under composition of addition. Okay, now what we're going to add on is the abelian criterion. Okay, and the abelian criterion is commutativity. So this says that for all little x and little y that you can possibly pick from the field capital F, it must be the case that if I add little x to little y, the answer is the same as if I add little y to little x. Okay, and what that basically says is that our addition composition table is symmetric down the diagonal line. Okay, so if I have the diagonal line there, it's beautifully symmetric down that diagonal line. Okay, so drawing a picture for this, this is of course called the commutative law, or rather the commutative law. I always put an extra tative in there, but you shouldn't. So here is our addition composition law once again. Okay, let's have these two elements marked on, little x and little y. So here is the row corresponding to little x, and here is the row corresponding to little y. And then similarly over here we'll have a column corresponding to little x and a column corresponding to little y. Okay, so if I take x plus y, that is this answer over here. Okay, so that's this one. Whereas y plus x is obviously a different entry in the composition table. It's over here. Okay, and basically those are each other's mirror image down this diagonal line here, and we're basically saying that those two have to be the same as each other for whatever little x you choose and whatever little y you choose, and that's the statement that the entire addition composition table is symmetric down the diagonal line. Okay, so those are the 5 axioms that the addition composition law must obey. Okay, and they can be summarised up, and indeed we will often summarise them up as saying that under addition the field has to be an abelian group. Okay, we'll have a break there, and in the next video what we'll do is address multiplication, the second composition.